Welcome back. All right, so we're going to keep talking about number bases here because there's a few other number bases that are sort of relevant in computer science. Now, before we do that, let's just kind of establish what we've gone over because we're going to be able to use what we've done to sort of figure out what's coming up. So, base 10. What digits are available to us in base 10? Well, we start with 0, and then we go up to 9. So we have 10 digits available to us, and those digits are 0 through 9. And then if we're talking about place values, all right, we have 10 to the 0, which is the ones place, 10 to the first, which is the tens place, 10 squared, which is the hundredths place, and so on and so forth. Now, base 2, the only digits we get are 0 and 1. So we have 2 digits, but they are 0 and 1. And then our place values are all powers of 2. Even though 2 isn't one of our digits, 2 represents our place values. So we have the ones place, we have the twos place, we have the fours place, and so on and so forth. So this is not exclusive to just base 10 and base 2, right? We can think of this as base n. This will work for anything. So in base n, the digits still start at 0. We always start at 0. And then from there, it goes to n minus 1. So we always start at 0. And we always stop at 1 less than the base. So if you were base 9, you'd have the digits 0 through 8. If you were base 20, you'd have the digits 0 through 9. And then the place values would just be n to the 0, n to the first, n to the second, etc., whatever n is. All right. And there's down here at the example, like Mayans use base 20. I'm not even going to try to say that right. In New Guinea, used base 27. Namibia used base 12. So there have been different cultures that have used different bases throughout time. Now, the other two big ones that we're going to see in computer science are base 8 and hexadecimal. All right, so these are the two that basically you're going to be responsible for in addition to base 10 and binary. So octal, base 8, based on what we just said, means that we're going to have, digits 0 to 7. All right, and these are all powers of 8. So this would be 8 to the 0, so that's the ones place. 8 to the first, that's the eighths place. 8 squared, that would be the 64th place. 8 cubed, that would be the 512th place. And 8 to the 4th would be the 4096th place. All right, so if we were converting this over and trying to turn 40173 base 8 into a base 10 number, all right, it would be 4 times 8 to the 4th, which happens to be 4096, plus 0 times 8 to the 3rd, which again, the 0 is just going to wipe it out, but 8 to the 3rd is 512, plus 1 times 8 squared, which is 64, plus 7 times 8 to the first, which is just 8, and then 3 times 8 to the 0, which is just going to be 3 times 1, because anything to the 0 power is 1. And then if we work those all out, it would be 16,507 base 10. All right, so in our number system, 16,507, it is 40173 in base 8. All right. Hexadecimal, same thing. The only difference is now you're seeing letters, and you might be saying to yourself, well, why am I seeing letters? Well, base 16 has the digits 0 to 15. All right. How do you start representing the 10 digit, the 11 digit, the 12 digit? We don't want to use two numbers. So that's where the A, the B, and everything else comes on. So we go to our digits for this one. We still start at 0, just like we always do. 1, 2. We get up to 9. And then to represent 10, that's where we start using A, B, C, D, E, and then we top out at F. All right, that's our 15th digit right there. All right, but again, the formula for breaking this down doesn't change. All right, this right here is our ones place, only this time it's 16 to the 0 power. This one is our 16's place. This is our 16 squared place. This is our 16th to the 3rd place. This is our 16th to the 4th place. So if we wanted to know what this equals in base 10, you've got 4 times 16 to the 4th, which is 65,536, plus F, remember, is 10, 11, 12, 13, 14, 15. So that would be 15 times 16 to the 3rd, which is 4,096, plus A, which remember, A is really 10. So 10 times 16 squared, which is 256, plus 7 times 16 to the first is just 7 times 16, plus 2 times 16 to the 0 power. Again, anything to 0 power is 1, so this is just 2 times 1. And if we worked all of this out and added it all up, we would get 326,258 base 10. So again, in our number system, 326,258. In hexadecimal, 4FA72, but these two numbers have the same value. All right, they're equivalent even though they look different. So why base 8 and base 16? Both are powers of 2, which means they have a connection to binary. All right, and they have a connection that's going to make our lives a little easier when we're converting back and forth. All right, and that connection is, let's just take this 40173. All right, one number in base 8 is equal to 3 binary digits. All right, 2 to the 3rd is 8. So what do I mean by one octal digit is worth 3 binary digits? So if you have a 3 in octal, this can, in binary, correspond to 0, 1, 1. All right, because in binary, that would be a 3. This 7 would correspond to 1, 1, 1. All right, 4, 2, 1. There's my 7. This 1 right here would correspond to 0, 0, 1. All right. The 0 would correspond to 0, 0, 0. And this 4 would correspond to 1, 0, 0. All right, so it's very easy to go back and forth between base 8 and binary. All right, so 1, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1 is the same as 4, 0, 1, 7, 3, which is the same as 16,507. All right, so it's very easy to go back and forth. And a lot of times we'll use base 8 and base 16 instead of writing out long strings of binary digits. It's easier to sort of condense them down into base 8 or base 16, and then it's very easy to stretch them back out to binary if you so choose. So base 8 is 3 binary digits. It's probably not going to be a surprise that base 16 is 4 binary digits. All right, so if I've got 4FA72, I could do the same exact thing, only now I'm using 4 digits to represent each number. So 2 would be 0, 0, 1, 0. All right, 7 would be 0, 1, 1, 1. A, which remember is really 10, means I've got a 1 in the 8 spot and then a 1 in the 2 spot. So there's my 10. All right. F is really 15. So that's going to be 1, 1, 1, 1. All right. 8, 4, 2, 1. That's where my 15 is coming from. And then this 4 here is going to be 0, 1, 0, 0. So again, this would be the binary representation of 4FA72, which is equal to 326,258. So this is what it is in base 10. This is what the number would be in binary. This is what the number would be in hexadecimal. So again, it's very easy to go back and forth between the two. And again, I could convert these. Like if I had a long binary number, I could look at the back 4 digits, turn that into a hexadecimal number. Look at the next 4 digits, turn that into a hexadecimal number. Look at the next 4, turn that into a hexadecimal, and keep going up. If you're going to do that, always start at the back because it does have to be in groups of 4. And if you start at the front and you do 4, 4, 4, you might not always end up with 4 in the back group. But you can always add zeros to the front. So always, if you're doing that, make sure you start at the back and go forward. All right, so these are 2 of the other number systems that we're going to see quite a lot in this class. So again, I'm going to put some practice up here. I encourage you to pause the video and do it on your own. But then I will kind of put the answers up there. So this is just a blank sheet. But the ones that I'm going to encourage you to do is take 2CA base 16, convert that to base 10. Take 745 base 8 and convert that to base 10. And then last but not least, take 1, 2, 0, 2, 1 base 3 and convert that to base 10. Now, we didn't specifically do a base 3 example, but follow the same logic that we've used for base 8, base 2, base 16, and apply that to base 3 and see if you can figure that out. All right, so here's where, again, pause the video, give it a shot. I'm going to now put the answers down, but hopefully you tried these on your own instead of just watching the video. So again, it can sometimes be helpful to just think about the places. So this is 16 to the 0. This is 16 to the first. This is 16 squared. This is going to be 8 to the 0, 8 to the first, 8 squared. And then this is going to be 3 to the 0, 3 to the first, 3 squared, 3 cubed, and then 3 to the 4th. All right. And then it's just a matter of kind of multiplying these out. All right. So when we're converting to base 10, generally what we're doing is we're multiplying. All right. So we're multiplying when we do base 10. So what we've got is 2 times 256 plus C, again, is the number 12 times 16 plus A is the number 10 times 1. And altogether, that should equal 714 base 10. Same thing here, all right? 8 squared is 64, so 7 times 64 plus 4 times 8 to the first is just 4 times 8, plus 5 times 8 to the 0 power is just 5 times 1. And again, all that should equal 485 base 10. And then over here on our base 3, 3 to the 4th is actually 81. So we've got 1 times 81 plus 2 times 27 plus 0 times 9. So that one's just going to kind of wipe out. Plus 2 times 3 plus 1 times 1. And that should all equal 142 base 10. All right. So hopefully you got those answers for this one. Again, nice question down here. Why do computer nerds confuse Christmas and Halloween? Because decimal 25 equals octal 31. Get it? 3 times 8 plus 1 times 1, because this is 8 to the first, 8 to the 0, equals 25. Boom. Computer science jokes. So good. All right. Let's talk about converting from base 10 to any other base. All right. So I give you a number in base 10 and I tell you that I want it in base 8. I give you a number in base 10 and I tell you I want it in base 3 or whatever. All right. So good news is it works the same way it worked for binary. All right. The greedy algorithm is a little more annoying for these. So we're not actually going to do it because with binary, the greedy algorithm is easy because it's either a 0 or a 1. It becomes much more challenging trying to do a similar approach with other bases because it's not just 0 and 1. So then you have to do more calculations and it's just easier to do the division. All right. So when we're going in this direction, we're generally going to be dividing and we're going to do the same exact thing that we did with binary. All right. So let's pretend we wanted to go from 490 base 10 over to base 8. All right, so we're going to go from 490 in base 10 over to base 8. We would start with 490 down here, and we would divide that by 8. And we would say to ourselves, oh, 490 divided by 8, that goes in 61 times. Now you might be saying to yourself, how do I know it goes in 61 times? Well, you can use a calculator. And then just ignore the decimal, and then all you have to figure out is sort of the remainder. But it does go in 61 times, and the remainder is 2. And then we can divide 61 by 8 and say, all right, how many times does 8 go into 61? And it goes in 7 times with a remainder of 5. All right, 7 times 8 is 56. 61 minus 56 is 5. And then how many times does 8 go into 7? Well, it goes in 0 times with a remainder of 7. The 0 is when we know to stop, just like it was for the binary ones. All right, which means we now read these top to bottom. And 490 base 10 is the same as 752 base 8. Okay. So let's do another one. Let's go 490 base 10 into base 16. All right. So again, I'm going to put the 490 down here. I'm going to divide it by 16. All right. How many times does 16 go into 490? Well, it goes in 30 times. 30 times 16 is 480, which means that my remainder is 10. There's 10 left over. And then I can divide by 16 again. 16 only goes into 30 one time. And then there are 14 left over. And then how many times does 16 go into 1? Well, it goes in 0 times with 1 left over. So again, this tells me to stop. And then I'm going to read this top to bottom. And I have to be careful here because I'm not going to write 14 and 10. I'm going to write 1. I'm going to say to myself, all right, 14 is actually E. And then I'm going to say to myself, 10 is actually A. So in base 16, 1EA is the same as 490 in base 10. And then last but not least, we'll do this one more time. 490 base 10 into base 3. All right. And base 3 isn't one we usually use, but it's just to show you how this can work for any base. All right. It's not something that only works for 8, 16, and 2. We can use this for anything. So I can do 490, divide that by 3. It's going to go in 163 times with a remainder of 1. I can divide 163 by 3. It's going to go in 54 times with a remainder of 1. And then I can just keep going here. This one's going to go in 18 times with nothing left over. This is going to go in 6 times with nothing left over. This is going to go in 2 times with nothing left over. This is going to go in 0 times, which tells me that I'm ready to stop. And there's going to be 2 left over. All right, so that tells me that 2, because again, we go top to bottom, 2, 0, 0, 0, 1, 1, base 3 is the same as 490 base 10, or 1EA base 16, or 752 base 8. All right. So again, we can use this algorithm to go in between any base we want. All right. We know how to get to base 10. And then once we're in base 10, we know how to convert it to any other base we want. So a lot of times, if we're dealing with a bunch of weird bases, you'll take it and you'll turn it into base 10 by multiplying, and then you'll use division to change it to whatever base that you want. And in that way, you can convert between anything you could possibly want to convert between. All right. So what I like to do now is just explain why this division algorithm works, because it's one thing for you to just be able to carry it out. It's another thing for you to actually understand how it works and what it's actually doing. So let's just pretend that we have 684 base 10, and we want to convert that to base 8. All right, so if I divide 684 by 8, I'm going to get 85 with a remainder of 4. If I divide 85 by 8, I'm going to get 10 with a remainder of 5. If I divide 10 by 8, I'm going to get 1 with a remainder of 2. If I divide 1 by 8, I'm going to get 0 with a remainder of 1. So that tells me that in base 8, 684 is 1, 2, 5, 4, base 8. All right, these two numbers are equivalent. So here's the theory behind how this algorithm works. All right, 684 could be rewritten as 1 times 8 to the third plus 2 times 8 squared plus 5 times 8 plus 4. All right, this calculation right here, this is equal to 684. We just kind of showed that using our algorithm. We just don't know it at the start. So when we start this process, all right, when we start this process, 684 could be this. We just don't know it. We don't realize that that's what this is, but it is. All right, that's kind of what we just went through when we did this. So when we're dividing by 8, what we're really doing is sort of pulling out the common 8 from these three terms and then recognizing that this 4 is what's left over. And when we pull out that common 8, all right, now we could kind of rewrite this as 1 times 8 squared plus 2 times 8 to the first plus 5. All right. And then I could say, all right, well, I'm going to pull out the common 8 here. All right. And when I do that, I then get 1 times 8 to the first plus 2. And then I could say, well, I could really sort of pull the 8 out of just this part, and I'd have the 2 left over. And then I've got just this 1 here, and there's no 1s to pull out there, so I'm at 0, and I've got my remainder 1, my remainder 2, my remainder 5, my remainder 4. So that's sort of the reason this works. All right, that's the reason we can do this division algorithm for any base, because this number could be rewritten like this, or it could be rewritten with powers of 16, or it could be rewritten with powers of 3. And then by just doing this repeated division, it's like we're pulling out those powers over and over again and just seeing what's left over. All right, so again, you don't need to do it this way. This is just showing you why this works. So it's not just some magic process that we do. We're basically just pulling out the powers over and over again and focusing on what's left over. And that's letting us kind of break it down into base 8. So again, just some insight onto why all of that works. All right, so with that in place, let's start kind of tying this back to computers. All right, so we've kind of been in this numerical world of bases and converting. Let's start tying this back to the actual computer. So in a computer, we have a bit, and a bit is our smallest unit of storage, and it stores a 0 or 1. All right, it's our smallest unit of storage. A byte is a group of 8 bits. So if you are trying to store a number on a computer and you have 1 byte to hold that number, the largest number you could store would be 1, 1, 1, 1, 1, 1, 1, 1. Because again, computers only work in binary. Which, if we're going through our powers of 2, this is 1, 2, 4, 8, 16, 32, 64, 128. Since those are all 1s, we can think of these as all being turned on, which means if we added them all together, we would end up with 255 base 10. So if we have a byte, the largest we can store is 255 base 10. Now, another way to know this, instead of having to do all that addition, is to say that it's 2 to the 8th power minus 1. So if we have 8 spots, the largest number we can represent is 2 to the 8th minus 1. If we had 10 spots, the largest number we'd be able to represent is 2 to the 10th minus 1. It's always 1 less than 2 to that power. All right, and again, so this would give us our 256 minus 1, which gives us our 255. Now, this 256 is significant because this is the number of unique let's say values we can represent. All right. So we can represent 256 different numbers, but those 256 different numbers range from 0 to 255. Because we have to represent 0, we don't get to represent 256. All right, so we only can represent 0 to 255, but that's a total of 256 unique numbers. And then the smallest number is a lot easier. That's just 0, 0, 0, 0, 0, 0, 0, which shockingly in base 10 is 0. All right, so the smallest number is a little easier to wrap your head around. All right, so again, just kind of tying it back to a computer here. Now, let's see if we can spot a general pattern, all right? And this is kind of what I was just saying, all right? But if we have 2 bits, the smallest number we can represent is 0. The largest number we can represent would be 3. If I have 3 bits, the smallest number I can represent is 0. The largest number is 7. 4, 0, and then the largest is 15. 5, 0. Again, the smallest is always going to be 0, but the largest is 31. 6 is 0. The largest is 63. 7 is 0. The largest is 127. So in general, if you have n bits, the smallest is still going to be 0, and then the largest is going to be that 2 to the n minus 1. All right, so again, 2 squared minus 1 is 3. 2 cubed minus 1 is 7. 2 to the 4th minus 1 is 15. 2 to the 5th minus 1 is 31, and so on and so forth. All right, so that's the general kind of formula you can use if I ever asked you what's the largest number you can represent with, so on and so forth. All right, just a point of interest here. In computers, numbers are typically stored in 16 or 32 bits. So what is the largest natural number you can store in 32 bits? Well, using our little formula, it would be 2 to the 32nd minus 1. All right. And I'm assuming most of you can do that in your head. But if you can't, it's 4,294,967,295. All right. So with just 32 bits, we can represent a massive amount of numbers. All right. And that's kind of that whole idea of like exponential growth when we were talking about like the growing pile of newspapers and stuff like that. So usually the next question that comes up is, all right, 0, but like not 0, like we need numbers smaller than 0. What about negative numbers? Now, one of the ways that computers can represent negative numbers is called sign magnitude notation. It's not the only way. All right, when you read the chapter on this material, you're going to see it talk about like 2's complement and things like that. But what we're going to focus on in this class, what you're going to be responsible for is sign magnitude. Right? And in sign magnitude, we just use the leftmost bit for the sign. So a 1 represents a negative number. A 0 represents a positive number. So to represent -5 with 8-bit sign magnitude notation, all right, this right here tells us that it's negative. And then this right here is a binary number. You don't really have to worry about the zeros. The 101 tells us that it's a 5. So that would be our -5. All right, so how about +56 with 8-bit sign notation? So sometimes it's helpful to just like kind of set it up and say, all right, here are my 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. This bit is responsible for positive or negative. And then a lot of times it's just easier to work from the back, but this would be my 1's place, 2's place, 4 place, 8's place, 16th, 32, 64th. All right. So because it's positive, I know that this is going to be 0. 64 is too big, so I know this has to be 0. I can use the 32, so that's fine. 32 plus 16 is 48, so we're still good here. 48 plus 8 is 56. So then that tells me the rest of these have to be 0. So 0, 0, 1, 1, 1, 0, 0, 0 would be +56 in 8-bit signed magnitude notation. Now, -56 is going to be the same exact thing, only that first digit, instead of being a 0, is going to be a 1. So it would be 1, 0, 1, 1, 1, 0, 0, 0. Only the first bit changes. All right. And then how about a -1 with 8-bit sign magnitude notation? Well, if it's negative, we know that the first digit has to be 1. That's our sign bit. And then 1 just means we're going to have a bunch of zeros. 1, 2, 3, 4, 5, 6. And then the last digit will be our 1 there. All right, so 8 bits or 1 byte. 1, 2, 3, 4, 5, 6, 7, 8. All right, so pretty straightforward. You just have to kind of remember that that first bit is going to be your sign bit. Now, a question that is going to come up a lot, you'll see this on your test, come up with the smallest and largest values using 3-bit sign magnitude notation. So basically, you're going to see a question like this at some point. It's just the number of bits that you are given is going to change. So we'll start with some smaller examples, and then we'll get bigger. All right, so count up from the smallest to largest value using 3-bit sign magnitude notation. So the smallest number that we could possibly have is 111. Because remember, that first bit is the sign bit. So this would be -3. Then we could have 110, which would be -2. We could have 101, which would be -1. Now, this is where it gets a little weird, but we actually can have 2 different representations of 0. We have like a +0 and a -0. And this is actually a little wasteful, which is why a lot of times sign magnitude notation actually isn't used, because you've got this double 0 here thing, and that can cause problems. But for right now, just accept that we have double zeros. We have 2 different ways of representing 0. And then we have 001, which is our +1. We have 010, which is our +2. And we have our 011, which is our +3. So in 3-bit sign magnitude notation, we can go from -3 to +3. Or another way of looking at this is the smallest number is -2 to the 3rd minus 1 minus 1. All right, and you might say to yourself, well, that seems really complicated. Yeah, but it's going to be easier once we're dealing with like 7, 12, 15 bits than trying to count everything out. All right, so it's 3 bits, so it's 2 to the third. We're subtracting away one of those because we had to waste a bit for the sign, and then we subtract 1 from that total because we have to represent the 0. So on the positive side, it would be the same exact thing, 2 to the third minus 1 minus 1. All right. All right, so that's how we can figure out the largest. That's how we can figure out the smallest. Again, it's going to be the same value, just one is positive and one is negative. And then the number of different values, well, we have 3 negative. We have 0. We're not going to count it as 2 different values because, again, they're both 0. And we have 3 positive, which means we have 7 total. Or another way of saying that is we have 2 to the third minus 1 total values. And the minus 1 is because we have 2 zeros. So if we're flipping back for a second, let me find the right sheet so that I'm drawing up what I wanted to draw up. Where is the right sheet? This is what happened. We've got too many sheets of paper. Oh, here we are. All right. So on this one, I said like, oh, the number of unique values is 256, which was 2 to the 8th. But we were representing 0 to 255. So if you're not dealing with signs and you have 8 bits, you get 256 unique values because you don't have that double 0. When you're dealing with positive and negative, you have to subtract the 1 because you are wasting 2 different sequences on just a single number. All right. So let's take a look at some more of these. All right. So this says count up from the smallest to largest using 32-bit signed magnitude notation. So again, this is where that little formula is going to come in handy because you're not actually going to want to count those. So if I had 32 bits, the smallest number is going to be 32 ones. Now again, the formula would be, that's going to be a negative 2 to the 32nd minus 1, because I'm wasting a bit on the sign, and then minus 1 again. So that's basically negative 2 to the 31st minus 1, which is negative 2,147,483,647. All right. And now the positive highest number would be 0 at the front and then 1s all the way to the end. And again, it's going to be the same exact calculation, just with a positive sign in front of it. So 2 to the 32nd minus 1, or a positive 2 to the 31st minus 1, or put another way, 2,147,483,647. All right. So once you start counting in positives and negatives, this is actually the smallest number you could represent using 32 bits. This is the largest number you could represent using 32 bits. And then if we wanted to figure out how many unique values we had in total, remember you've got your negative values and you've got 2 to the 31 minus 1 negative values. Even though we have 2 representations for 0, we've only got 1 0. There is no such thing really as a negative 0 and a positive 0. And then we have 2 to the 31 minus 1 positive values. So altogether, that's actually 2 to the 32 minus 1. Because again, we're using 32 bits, but we're subtracting away the double 0, which means we have 4,294,000,000 967,295 unique values. The largest of which is this, the smallest of which is this. And again, we're shorted one value because we end up having two representations for 0, but it's only a single value. All right, we don't count it as two separate values. All right, so I think this is probably a good place to pause it. Again, let me know if you have any questions, and then we'll go from there. All right, have a great day, and I will talk to you later.